Thank you everyone coming for another series of our NL seminar. Today we have Yihan Wang from UCLA. She's a PhD candidate in the Department of Computer Science, advised by Professor Cho J. Xie. Her research interest is in trustworthy and generalizable machine learning. She is one of the recipients of the 2023 UCLA Amazon Fellowship. Can't wait for her talk today on detecting language models. So,
thank you. I'm very happy to be here today to introduce our work red teaming language model detectors with language models. And this work is done with another two co-first authors, Zhou Xinfan, and our advisors, Kaiwei and Chou. So we all know that now there are many large language models available to the users around the world. But along with this wide use of large language models, there are also some misuse of these tools, even if they are not allowed. For example, some students may use the large language models to write their homework, and some malicious users may use them to generate some misinformation and post them on the internet. And also some malicious users can use them to generate some scamming emails. And even if the intent of the users is not malicious, this machine-generated text will be posted on the internet, and it will contaminate the future training of the future language models, which is the data contamination. And this is why we need the language model detectors to detect the text generated by machines and remove this text if this is necessary. And there are three main kinds of most popular language model detectors: the watermarking-based detectors, including the token level and sentence level. And I think currently the token level watermarking is the most popular one and most reliable one. And the second type is the classifier-based detectors. The classifier-based detectors train for example, a neural network-based classifier to predict whether this text is generated by machine or generated by human. And I think in 2022, OpenAI has released a text classifier to classify the text generated by AI, but now it's not available. This classifier was taken off around August in 2023. And I think they also found that this classifier is not reliable enough. But there are still many online language model detectors. And the third type is the likelihood-based detectors, and more specifically, the DetectGPT. And I will introduce these three types of most popular language model detectors in detail later. So the problem is that are these detectors robust enough? Some existing works have shown that paraphrasing is effective enough to bypass these language model detectors. And there are many paraphrases available online or open source on GitHub. But the problem is that these paraphrases can also be detected by detectors. For example, we can still train an NM-based classifier to predict whether this text is generated by non-paraphrases. And we can also add watermarking into these paraphrases, and then we can detect. So in this work, we consider a stronger setting. We only use language models that are protected by detectors. Here, the protected means that the generated text from these language models to be used in adversarial attack can still be detected by some detectors. And we will show that even under this stronger setting, we can still generate some adversarial attacks by these large language models, and these attacks are difficult to be detected. And this is overview of the talk today. I will introduce the attack against the three most popular types of language model detectors. And finally, I will have some discussions and some possible future works.
Just to be clear, your goal is to make text that cannot be detected. Right?
Yes. So the first detector I'm going to talk about today is the token level watermarking. And I think this original paper has won the best paper award at ICML, so it's very popular right now. The intuition of the token level watermarking is that they divide the vocabulary into a green list and a red list, and they divide the vocabulary randomly. For example, in this example, they keep the 50% of the tokens to be in the green list and the other 15% to be in the red list. And if the generation model has no knowledge to this green list, then the green list tokens and the red list tokens will uniformly distributed between the green list and the red list, and as shown in the no watermark example. But if this text is generated with watermarking, then there will be more than 50% of green list tokens. And then we can detect the watermarking with a z-test. So here in this z-score formula, the length of the text is t. So the expectation of the number of green list tokens is t over 2. And if the number of green list tokens in the text is much larger than t over 2, then it means that the probability of the text to be generated with watermarking will be very high. And so in a general case, they hash the they divide the vocabulary according to a hash value on the existing prefix. And they can show the ratio of the green list token to be a hyperparameter gamma. So if the gamma is small, it means that the green list is also smaller, and the watermarking will be stronger. And then they will increase the probability of green list tokens in generation by adding an offset delta in the softmax. So we can see that in this strategy, only tokens with a higher entropy will be impacted in decoding. Because when they design the watermarking algorithm, they do not want the watermarking to impact the generation process too much and harm the generation quality too much. But this can also be utilized to identify tokens that has a higher probability to be impacted. And then we can replace these tokens to generate an adversarial attack. So this is a query-free attack on watermarking. The input is a text S, and X is generated by a watermarked large language model, and the length is N. And we also have an attack budget epsilon. So in this adversarial attack, we can replace or perturb at most epsilon multiplies N tokens, because we want to maintain the semantic meaning. And we also have the access to the target model N. So at step 1, we saw the tokens in S by its entropy, evaluated by the target model M. And because the tokens with a higher entropy, we have the higher probability to have been impacted by watermarks. So now we will replace the top epsilon multiplies N tokens with highest entropy with some reasonable word substitution candidates.
So you have an assumption here that you have the token probability of the model, right?
Yes.
And you have an assumption that you know what the green and the red lists are?
We do not know whether the token is in the green list or not. So the next question is that how can we get a reasonable substitution candidate? observation is that even a watermarked large language model can still generate reasonable substitution candidates for a given token. So here we prompt a llama model with watermarking. And we can say that the model can still generate, can still suggest some reasonable synonyms for this word exciting. And the reason is that if we want to apply watermarking to a language model, we still need to maintain the OK generation quality. So some simple tasks such as generating some synonyms should not be impacted. And this is the attack result. Here we report the AUC, and DR is the detection rate before and after the adversarial attack. And we have a baseline attack, which is the paraphrasing. And the data paraphrasing is released by another paper, and they say that paraphrasing can attack the watermark detection as well. Okay, and the second type of
Go back to the last slide and give us a takeaway message.
Yeah, the takeaway message is that with this query-free word substitution, we can significantly decrease the detection rate and also the AURC. So the AURC before the attack is very high. It's close to 100, it's over 95. And then I think, and after the attack, the AUC will be decreased to like 60, 70, and 80.
So these are data sets that are even, like AI5 is like a Reddit data set.
Yes.
Right. And so in some cases you're doing generated explanations. In some cases you're using human explanations. So this is like the test. So for detection rates, for example, the detection is llama or not llama or human, basically, right? And so is your data set then like a test set where it's like 50% of the data is by llama, 50% of the data is by human, and the idea is to classify which is which?
Yes, we keep we use the ground truth. We use the human response from the LLM dataset as the human text dataset.
Okay, and then the generated data set.
And the generated dataset is generated by the watermarked.
Oh, do you have two completions for each prompt?
But in this experiment, the compilation response is from the watermarked llama.
Yeah, you have watermark llama and human.
Yes.
And your model is trying to classify. You're trying to detect which one. You're taking the watermark llama and then you're regenerating from it, right?
Yes.
And then you're saying, okay, now compare that to human.
Yes.
And kind of classify or detect, which is, can a watermark based classification attack detect, right? So like, yeah. How do you guys score, for example, 16 in the lower right corner? What is a 16?
So the unattacked. So for the unattacked number, we generate a text using the watermarked large llama. And we also have another data set with a human text. And then we compute the AURC to distinguish between the watermarked llama generated text and the human text.
So what is this AURC? How do you calculate that? Like you have it's got to be some kind of model that's deciding it's GPT, it's llama versus it's human. Right? And that model itself presumably is using, I don't know, it's a model using watermarking to do it?
The detector is using the z-test, the z-test. So the z-test will have a score, and we can adjust the threshold on the score to compute the AURC.
Okay, so basically what you're saying is that your outputs have basically a roughly 50% mix of green and red.
Mhm.
But you're not actually evaluating whether or not the data has changed in its meaning. Like you could just, like the output of any text could be bits per, right? Alternating, which would have a 50% read, 50% read, but it would be no totally wrong.
Yes, we do not change the semantic meaning.
How do you know?
We have done a human evaluation at the end.
Okay.
Yeah. Yeah, I think the human evaluation part is at the end of the talk, and I will show later. And the second type of detector is the detectability. And their implication is that the language model generated text will tend to lie on the local peak of the likelihood surface. And this is intuitive because in language model decoding, we want to decode the text with the highest likelihood. So this figure is copied from the detectability paper. And the X fake is a language model generated text. And the black curve is the likelihood curve evaluated by the target model. So the text generated by the language model will be on the local peak. So if you add some random perturbation to this language model generated text, it will be perturbed away from this peak. So for example, the X1, 2, 3, 4 here. But if this text is generated by human, it will not be that optimal. So it will be lie on a random place on the likelihood surface. And if you add some random perturbation to this human generated text, you will not observe a similar pattern as the machine generated text. So the detectability utilizes this observation. And in their algorithm, they generated the random perturbed copies by some sample replacement or masking. And then they evaluate the log likelihood of the perturbed copies. And then they compare the difference between the likelihood of the original text and the likelihood of the perturbed copies. And if the difference is large enough, then they predict that the text might be a model sample. And if the difference is not very significant, then they predict that the text might be generated by a human. So, but this strategy is also very easy to be attacked from their intuition. And just a random word substitution can effectively attack detectability. Because in their assumption that a machine learning generated text is around the peak. So if you add some perturbations onto the X peak, you're moving the X peak away from the peak. And if you can successfully move the X peak away from the peak, then detectability will not work. So we found that even a random word substitution can work. And the attack performance can even be further boosted if we use a genetic attack to move the X peak to be much more away from the peak. And this is the result. So here the query-free substitution means a random substitution. We just randomly sample some tokens and replace these tokens with a word substitution suggested by the model. And the query-based substitution is a genetic-based algorithm. So we use genetic optimization to find word replacements to minimize the predicted probability. And we can see that even the query-free substitution can significantly reduce the this table should be about the detection rate. So even the query-free substitution can decrease the detection rate significantly from, for example, from 80% to 25%. And if we add the genetic attack, the detection rate can be reduced to even around 0.
So that's definitely going to change the semantics, right?
Yes, but we still have a budget, a perturbation budget. So we only perturb around 10% of the tokens.
Okay, but that's like 2 words in an average sentence, right? So like if I'm reading a sentence and it has 2 completely out of nowhere words,
Yes,
in zebra the sentence, then I'm going to know that the thing was generated by the machine.
yes, but
As a,
the replacement candidate is, for example, is generated by the model itself.
I think there's a random generation.
The random here means that the token to be replaced is randomly chosen.
But you're still replacing according to the model.
Yes. And the third type of the classifier is NN-based classifiers. And I think the NN-based classifier is the most widely used online. And they are, for example, the OpenAI released classifier has been taken off. But there are still lots of NN-based classifiers available online. And we try to do some experiments on this online classifiers when we are doing this work, but we find that they are not free, and they are very expensive. But the language model built with the neural networks and transformers are known to be not robust to adversarial attacks. So to begin with, we apply some existing attacks, like the random word substitution, and same as the previous one. Here, the random word substitution means that the token to be replaced is randomly chosen, but the substitution candidate is generated by the language model, and also the genetic attack. And here is the experiment result. The instructional prompt is a net attack, and I will introduce later. And here we can see that with query-free and query-based word substitution, the AAU, ROC, and detector rate can be significantly reduced. Especially the query-based substitution is very effective. Yeah.
Can you elaborate a bit more on what the query-based substitution is? Like, what is the genetic attack?
The genetic attack is like, so in each iteration, we have some random perturbation. We have some random word substitution onto the text, and we have multiple perturbed candidates, and we will evaluate the probability. We will evaluate the output of the classifier, and we will generate the candidate for the next iteration based on the candidate with the lowest score. Yeah. But this type of word replacement attacks can still suffer from some unnatural word replacement, even if we use the word substitution candidate generated by the language model. So our next question is whether we can find a better way to attack NN-based classifiers and generate more natural adversarial attacks. So before jumping into the methods, first we can think about how are these NN-based language model text classifiers are built. So if we want to train a classifier, we need to collect the training set with text generated by the target model. And we also need to collect some human text. And we label the text generated by the model to be 1 and the human text to be 0. And now we can train the model on this classification task. But the problem is that the coverage of the model generated text in this training data set is very essential. And if the NN-based classifier is applied on some text that is not sufficiently covered in the training data set, the performance can be worse on this out of distribution data. And some works have found that adding some keywords into the user prompt can make the performance of this classifier worse. For example, we can add some keywords like vivid, creative, emotional, and then the performance of the detectors will be less reliable. So how can we automatically search for such prompts? And I will introduce the algorithm itself later, but here I want to show an example first. So assume that I'm now a student and I was asked to write an article to answer this question. While we don't yet have a cable provider that will let me pick and pay for only the channels I want. And if I simply copy this question into ChatGPT and then copy the answer from ChatGPT, we will get the original response. I only keep the first sentence here for the limited space. And if I just copy the response from the ChatGPT, then the probability that this text will be identified from the classifier will be very high. So instead of using the response directly, I append a search instructional prompt after the user prompt. And in this instructional prompt, it has two parts. At the first part, the prompt asks the model to mimic the writing style of the given reference text. And the second part is a searched reference article, which is expected to be out of distribution and will be difficult for the classifier to identify. And now we can get a new response with this prompt. And we can see that the new response the new response is mimicking the given reference successfully. So here, for example, here the reference using some phrases like is still true, and the new response is also doing that. So in this algorithm, we want to search for the two parts. The first part is an instruction part, and the instruction part will ask the model to follow the writing style of the reference. And the second part is a reference for the already writing style. And this is the algorithm. We search for the instruction prompt and the reference prompt iteratively on a small training data set. So for our experiment, we do the experiment on, for example, we do the experiment on XSUM and AD5. And both the XSUM and AD5 data sets have a training set and a test set.
Wait, do they have instructions also, like style instructions?
No.
We can talk about that.
Yeah. So these two data sets only have the normal input and output. And the instruction and the reference will be searched during this algorithm. And the algorithm has, for example, we want to run this algorithm for 10 iterations. And in each iterations, we first optimize the reference given the current best instruction. And then we update the instruction given the current instruction and reference. So in each iteration, we first search for the reference part. A key component of the search for reference function is that here we have a priority queue here. The priority queue will contain the candidates of the reference articles generated in previous iterations. And in this priority queue, the reference candidates will be sorted according to their score evaluated by the target detector. So we want to find the articles that has the most out of distribution writing style, and that will be given a lower score from the classifier, from the target classifier.
Wait, sorry. So CREF, those are all human written.
What?
The CREF, all of the things that you're searching when you're searching for a reference.
Yeah.
Those are all human written, right?
The reference is also generated during the search.
The reference is generated.
Yes. So let's think about the first iteration. So the first iteration, we have an initial instruction. The initial instruction is written by human, and it's just please mimic the writing style of the given reference. And there's no initial reference article. And then at the first iteration, we search for the first reference article by generating. So at the first iteration, we generate some reference articles. And then we sort the generated articles by its scores received from the classifier. And then we keep the generated articles with the lowest score as the reference article for the next iteration. And then we update the instruction.
Okay, so you're generating a bunch of sentences, and whichever one the classifier thinks is least likely to be a robot.
Yes.
You use as the canonical style.
Yes.
Got it. Okay. You could also just like use some human generated sentence, right?
Yeah, it's possible, but I think it may also work if we have a large data set of human written text, and we keep the text that has the lowest score.
Right. And you have an infinitely large set of human generated text, right? Project Gutenberg.
Yeah, but for example, if we want to use it for another data set, and maybe another data set doesn't have a human text. So
why does it have to be from the same case? You could just use sentences from novels.
But no, we found that it's dependent on the data set, and a reference article generated for one data set may not work for another data set.
Okay.
Yeah. For example, if the reference and the question is too different. For example, the reference is writing a novel, and the user prompt is writing some scientific thing. Then the model will just refuse to follow the reference, or it may just copy some sentences from the reference article, but not mimicking the writing styles. And this is the attack result. The instructional prompt is not the most effective one, but I will show later that the generation quality from the instructional prompt is better than the query-based substitution, because the query-based substitution will have a larger impact on the naturalness of the text. And here is the human evaluation part. We have two metrics for the text after adversarial attack. The first is the fluency. Fluency asks the annotator to evaluate whether the text is grammatically correct and fluent. And this metric is important because we include some attacks such as word substitution. And in word substitution, it's very likely to result in some grammatical errors. And the second is about the plausibility. And this metric measures whether the generated text is plausible, which it means whether the generated text is answering the user input, not generating some unrelated content. And here the human evaluation results.
What's the range?
The range is so we have 5 annotators, and
What's the highest score you can get for fluency and plausibility? What's the lowest score?
the range should be 1, 2, 3. The high score 3. The lowest is 1.
And they have to get a whole number?
Yeah, the 1, 2, or 3.
So if plausibility given the input, you're not looking at, so you know, in all cases when you're doing a when you're attacking the detector, you're taking the original generated output and changing it to something else, right? So you have so unattacked, for example, is like llama generated text, right? And then all the other things are you start with llama generated text and then you make modifications to it.
Yes, for the word substitution, it's that case. But for instructional prompt, it can be very different from the original response, because
right. So you're not comparing to the original response.
No, we just give the user prompt and the response.
As if the user only ever saw the attacked approach.
No. So the annotator only have the user input and the response, and no any other information. So for the only AI text detector part, we have four attacks. The ChatGPT paraphrasing is just ask the ChatGPT to do some paraphrase. And query-free substitution is the random word substitution, and query-based substitution is the genetic attack. And instructional prompt is is using the search instructional prompt from the training data set and applied on the evaluation set. So we can see that the instructional prompts can have a better fluency compared to the query-based substitution on both of the 2 data sets.
Did you try asking what they thought about human outputs?
No.
You get to see if they actually find it more fluent and more plausible.
Yeah. That's a good suggestion. Yeah, and for the word substitution, even though we have used the word substitution candidate generated by the language model, we can still observe some decrease in the fluency measures.
What is the quantity after plus minus? After plus minus, is it error of the mean or standard deviation or what?
The plus and minus is the variance between different annotators. So we have 5 annotators.
Okay.
Yeah, and this is the mean and this is variance across different annotators. So the variance is relatively high actually, because the fluency and the plausibility is an objective measure. And we also have some comparisons across the 3 different detectors. So on the 3 figures, the blue one is the detector curve without attack. And the first one is for watermarking, and the second one is for the OpenAI detector. And the third one is for Detect-GPT. And the curve of other colors is for different attacks. And we can see that watermarking detector is the most robust one, and it is impacted less compared to the other 2 detectors. But the watermarking is also the only one that alters the generation process and may harm the generation quality. And recently, there are many new works about the trade-off between the generation quality and the detection performance for watermarking, and also for how to improve this trade-off. And I think recently many people are working on that, how to make the trade-off curve between quality and detection rate better. So the key takeaway is that the current popular language model text detectors are not robust, even under the strongest setting, where other strong language models may be protected by some text detectors. And among all the 3 current methods, watermarking is the most robust one, but it also suffers from some decrease in the generation quality. And our lab is also working on some ongoing and new directions on trustworthy large language models. So the first one is closely related to this work. So it's how to improve the trade-off between quality and detection performance of watermarking. And here is a report from an undergraduate of our lab. And we tried to improve the generation quality of watermark language models by identifying the tokens with a higher importance and keep those tokens during watermarking. And another thing we are focused on recently is how to design a stronger jailbreaking attacks, and also how to defend the large language model from the jailbreaking attacks. And recently we have a project on better denoising methods to remove the adversarial component in jailbreaking prompts. And this work will be on archive soon. Yeah, this is all for my talk today. Thank you.
I'm curious, so with watermarking, the quality of the generated output is a bit suboptimal compared to just pure generation, right? Mm-hmm. But that makes it easier for detector models to detect. Mm-hmm. But then your finding is showing that if you do substitution that leads to less natural text, it becomes more difficult to detect for the detection model. Is that the right kind of conclusion here? Because in your, if you go back in the human evaluation results, the query-based substitution and the query-free substitution, they have lower scores for fluency, and I think for plausibility, indicating that these methods lead to texts that are less natural. But then this also makes the detector more difficult. You've shown lower detection rates for these approaches too, right? So I'm saying that it's kind of strange that watermarking leads to text that is less natural, but that makes it easier to detect. But then perturbing that text to become more unnatural makes it more difficult to detect. Is kind of interesting.
Yeah, and are you talking about this one or the first one?
I'm talking about that one, I guess, yeah.
Yeah.
But I think the trend holds for both cases, yes.
Yeah, this is an interesting problem, interesting question. I think the thing is that the detectors are not dependent on the quality of the text. They are trying to they try to classify the responses according to some patterns, but the patterns may not be related to the quality. Yeah.
I think in your question you were assuming that watermarking is successful because there is a quality degradation in the generated text, but I think it's just only a side effect of limiting the vocabulary.
Yeah.
If we had a perfect world where the remaining vocabulary was still strong, the quality would decrease.
So there's a couple of different dimensions here. There's this, how little do you change the meaning to make it, not feel plausible, and then also how good are you at avoiding detection. But then also, so like, let's say I want to use your stuff, right? So I'm a student and I want to cheat, and so I'm going to generate data using some kind of attack approach to prevent you from evaluating my output and determining whether or not I cheat. But I don't know what method you're going to use to detect, right? So what approach should I use?
I think from this experiment, we just found that just randomly sample some tokens and replace them with some reasonable substitution candidates will effective enough.
So not the instructional prompts then.
The instructional prompts is only, I think the instructional prompt is only effective for the NN-based detectors.
Yeah, but you might use an NN-based detector.
Yes, I think that in this case, the instructional prompt will be effective. But the problem is that you need to search for an instructional prompt before you use it.
Yeah.
And the search process can be expensive.
But also, the instructional prompt is the only approach that doesn't require me to know the probabilities of my tokens.
Yes.
So if I want to use like GPT-4,
yes,
that's like I can only use instructional.
Yes.
But
you can also use a query-free substitution. So query-free substitution.
No, because you have to choose a replacement token that's probabilistically valid, right? Or so you ask for a substitution.
Yeah, we ask for substitution.
Gotcha. Okay, good to know.
Awesome. I think we had a lot of questions throughout the talk, so I think that's all of it. So let's give Yihan another round of applause.